So this video is on modelling. So I've made a video entirely dedicated to modelling for this chapter because I think this is the first chapter where there's a big emphasis on modelling. So just remember that modelling is applying what we've learned to real life scenarios. So just a couple of things for modelling differentiation. First of all, we've talked a lot about dy over dx being the gradient. Of course, that's what it is. But the more technical definition of dy over dx is how much y changes when x increases by 1. Now, of course, the variables might not always be y and x. So, for example, let's say that we have y is equal to x squared. So dy over dx is equal to, so what dy over dx actually means is the top term here is what's being differentiated. So we're differentiating y, and because y is equal to x squared, we're differentiating x squared. And then the term on the bottom is what we're doing it in terms of. So we're doing it in terms of x. We're differentiating the x part in x squared. So dy over dx for this is equal to 2x. So let's say that we have another function, and let's say that v is equal to 2t to the power of 3. dv over dt means that we are differentiating v, so we're differentiating v, so therefore we're differentiating 2t to the power of 3, and we're doing it in terms of t. So dv over dt is equal to 2 times, and then t3 differentiated is 3t squared. So this is equal to 6t squared. So just remember that they can use different terms, and the term on the top is the kind of y variable, and the term on the bottom is so-called the x variable. Another thing I just want to exaggerate quickly is stationary points. So remember, a stationary point, as we talked about in the last video, is when dy over dx is equal to 0. So this means that at this position, as we saw in the last video, there will be a maximum or a minimum, and this comes up quite a bit. They might want you to find the maximum or minimum of something, and to do this you find the derivative, set it to 0, and therefore you find the stationary point, you find the value of x for that stationary point, and then you can confirm if it's a maximum or a minimum, usually by a second order derivative. There'll be loads of examples of this in this video. Now finally, quite a common thing they might want you to do is to create an equation using the information they give you. Now I remember when I was doing A levels, I used to find this really hard. I thought this was quite ridiculous, but now looking at it, I don't actually think it's that bad at all. Maybe I just wasn't taught it properly or something, I don't know. But basically, they're going to give you some information, and it will usually be revolved around some sort of shape, and then they're going to give you the area, and then basically you can find the area or the volume with all the lengths of the sides that they give you, and then you can use this to make an equation. So here's a really basic example. Let's say that I gave you a cylinder, and let's say I said that the radius of the cylinder is equal to r, and the length of the cylinder is equal to L, and I told you that the volume of the cylinder is equal to 10, and I want you to give me an equation for L in terms of R. Well, the way that we can do this is by using the formula of the cylinder. The volume of a cylinder is equal to pi r squared L. You kind of need to know the volumes of some kind of basic shapes of like 3D shapes, so like this one for example. So we're told that we know that the volume of a cylinder is pi r squared L, but we're told that the volume is equal to 10. So what we can do is sub in all the sides that we know for the volume, equal this to 10, and therefore we have an equation, and therefore we can rearrange to find L in terms of R. So let's do this. So it's going to be pi, and then r squared, well the radius is just r, so we're just going to call this r squared, and it's the same for L, is equal to the volume, which is equal to 10. And now we have an equation, and we can rearrange this to find L in terms of r by just dividing both sides by pi r squared to get L is equal to 10 over pi r squared. So this is a very common exam questions. There's going to be loads of examples in this in the questions upcoming where they give you some sort of shape and you have to make an equation with the information you're given. So now I'm just going to go through quite a few questions, so to kind of give an idea of what kind of questions they'll ask and how to approach them, stuff like that. So here's an example from a past paper. So before you do any of these questions, I would always advise you to read through the kind of text part of the question and make sure you understand everything that's going on. So it's a modelling question where it kind of like has a real life application. It talks about like a letterbox and stuff like that. But read through the maths bit and make sure that all of the information is inside the diagram here. And all the information is inside. It talks about the lengths of all these sides here and these angles here to show that it's a prism. And it says that the volume of the letterbox is 9,600 centimeters cubed. So the volume is equal to 9,600. And this is useful because when, as I talked about in the intro, we can use this in order to create an equation, because we can find the volume of this prism and then equal it to 9,600, and therefore we can create an equation which hopefully it should be able to give this here, which is what we're looking for. Okay, so the volume of a prism, as I said in the start, you need to know the volume of some kind of basic shapes. The volume of a prism is always whatever the area of this side is here, which is this side here. So whatever the area of this is here, multiplied by the length of the prism. So the area of this side here multiplied by the length of the prism. Well, we know the length is y here. We just need to find the area of this here. Now this is a trapezium. You could use the trapezium formula if you want to, but a way that I would do it is just separate this into a rectangle and a right angled triangle, and then figure out the area of these two shapes individually, and therefore do it from here. So let's do that. Okay, so the area of this rectangle is going to be, so this side is 4x and this side is 6x, so therefore the area is going to be 4x times 6x, which is equal to 24x squared. And then the area of this triangle, well, this here is going to be the base, and this is just going to be 4x, it's the same side here. And then this is the height, and we know that this is 9x and this is 6x, so therefore we can figure out this height is just going to be 3x is 9x minus 6x. So therefore the area of this triangle, remember it's half base times height, so it's going to be half times the base, which is 4x, times the height, which is 3x, which is equal to, and I'm just going to multiply these to 2x times 3x, which is equal to 6x squared. So therefore the total area of this shape is going to be these two areas added together, 24x squared plus 6x squared, which is equal to 30x squared. So we know the area of this side, and therefore the volume is going to be this area, so 30x squared times the length of the prism, which is y. So times y, and obviously we can just write this as 30x squared y, and then we can equal this to 9,600. This is the very typical exam question which I was talking about at the start. We found the volume of the prism using the information given to us, and therefore we can equal this to the volume that's given to us, to 9,600. And therefore we need to show that y is equal to 320 over x squared. So we need to make y the subject, and hopefully it should be able to give this. So let's just do that and divide this side by 30x squared, or divide everything by 30x squared to get y is equal to, so I'm going to move this onto the other side to do 9,600 over 30x squared, which we can simplify because the 9,600 can be divided by the 30, and if you put that into a calculator, that is equal to 320 over x squared. So we've got y is equal to 320 over x squared, which is what's required. So for part B, we need to show that the surface area of the letterbox, which is called S, is given by this equation here. So the surface area is going to be all of the areas of all of the faces added together. Okay, well, we already know the area of two of the faces because we figured it out before, the area of these two trapeziums here, because we figured out the area of this as 30x squared. So therefore this is going to be 30x squared times 2, which is equal to 60x squared. So now we just need to figure out the areas of all of the other four sides. Okay, so let's do it one by one. So let's start with this side. So the area is going to be y, because this is one of the sides, times this length here, which if you look at this diagram here, you will see that this is 6x, the length of this side. So this is going to be 6xy. Let's do this face up here. So this is going to be, again, it's going to be y because this is the length of it. So it's going to be y times, and then it's going to be this length here, which is equal to 5x. So this is equal to 5xy. the area of this side is going to be, again, it's going to be y because that's the length, times, and it's going to be the length of this side here, which is going to be 9x. So this is equal to 9xy. And then the area of this side or face at the bottom is going to be y times the length of this side here, which is 4x. So this is going to be 4xy. And then the surface area, which is called S, is going to be all of these sides added together. It's going to be 60x squared plus, because of the two trapeziums, plus 6xy plus 5xy plus 9xy plus 4xy. We can simplify this by adding all the xy terms together, which is going to be 6 plus 5, which is 11, plus 9 is 20, plus 4 is 24, so plus 24xy. But you'll notice that there's not actually any y terms in the equation that they give us, and this is because we can use what we did last time. We found an equation for y in terms of x, so we can sub this in. So it's going to be 60x squared plus 24x, and then y is equal to 320 over x squared. We can simplify this further. Let's do 60x squared plus, and then 24 times 320, if you put it into a calculator, is equal to 7,680. And this is going to be over, and then x divided by x squared in the denominator is going to be x in the numerator. So if you want to, you can write 320x squared as 320 x to the minus 2 if you want, and then times this by x to show that it gives x in the numerator, but hopefully you can see that in the denominator, sorry. But hopefully you can see that by timesing x times x squared in the denominator gives this, and this is the final equation. So S is equal to 60x squared plus 7,680 divided by x. So for part C, we need to use calculus to find the minimum value of S. I don't know if I actually ever mentioned this in the videos, but calculus is basically just differentiation. It's also integration, which we see in the next chapter. So as it's the minimum value, this tells us it is going to be, as I said in the intro, it's going to be the stationary point. So we're going to have to do differentiation. So firstly, I'm going to rewrite this in the indices form. So it's going to be 60x squared plus 7680x to the minus 1. And then ds, because we're differentiating s over dx, because that's what we're differentiating by, is going to be equal to, and then we differentiate the terms individually. So it's going to be 60 times 2x, which is equal to 120x, and then it's going to be 7680 times minus x to the minus 2, which is equal to minus 7680 x to the minus 2. The ds over dx is equal to 120x minus 7680 x to the minus 2, and because it's the minimum value, it's going to be a stationary point, so this is going to be when the derivative is equal to 0. I'm going to rewrite this in the fraction form because I think it's a bit easier to work with. Minus 7680 over x squared, and this is when it's equal to 0. Now, as we have x in the denominator, we know that x cannot be 0, and therefore we can times everything by x, because remember, if x could be equal to 0, we can't do this because then we're timesing everything by 0 and then it just goes wrong. But because we know that x is not equal to 0, we can do this. I'm going to times everything by x squared to get rid of this denominator, so it's going to be 120x cubed minus 7680. This is equal to 0. Move the 7680 onto the other side to get 120x cubed. It's equal to 7680. Divide both sides by 120 to get x cubed is equal to, and it's going to be 64, and then x is going to equal the cube root of 64, which is equal to 4. It's not going to be plus or minus because that's only for even powers, so to the power of 2, to the power of 4, to the power of 6, etc. So x is equal to plus 4. So we know the x value for where the minimum value of s exists, so now we just need to find the actual minimum value of s. Now really quick again, we can check whether this is the right answer by using the d over dx function in our calculator, by putting this into our calculator and then hoping that when we put x equals 4 into the value of when x is equal to something, it should give out that it is equal to 0, and it does do that for this, so therefore this is a really good way to check that we've got the right answer. So now we need to find the minimum value of s, so that means we just sub in this value of 4 into this equation. So s is equal to 60 4 squared plus 7680 over 4, and if you put this into a calculator, this is equal to 2,880. So this is the minimum value of S, and this is the final answer. So for part D, we need to justify that the value we found is a minimum. And of course, we don't know this because we found when ds over dx is equal to 0. So we know there's a stationary point in there, but we don't know if this is a minimum, a maximum, or a point of inflection. So it specifically says by further differentiation, so we have to do the second order derivative, not the kind of analysing the points around x. So we have to find the second order derivative and then plug in x is equal to 4 where the minimum is, and this should give a positive number, which therefore proves that it's a minimum and not a maximum or a point of inflection. So we have to find the second order derivative, so it's going to be d squared s over dx squared, which is equal to, and then differentiate the terms individually, so it's going to be 120 because the x goes away, and then it's going to be minus 7680 times, and then this differentiated is minus 2x to the power of minus 3, which is equal to, minuses cancel out, so it's going to be 15360x to the minus 3. So d squared s over dx squared is going to be 120 plus 15360x to the power of minus 3. And then we sub in x to the 4, so 120 plus 15360 4 to the power of minus 3, and if you put this into a calculator, this is equal to 360, which is a positive number, so therefore as it's positive it's a minimum. It's not a maximum of a point of inflection as it's bigger than 0, the second order derivative. So that's the final answer. So here's another question on modelling. So as I said at the start, a good thing is always to read through the questions, make sure you understand everything that's going on. So we have a cylinder and it has a volume of 75 pi, and we're told that the radius of the cylinder is r. So let's just draw a quick diagram. So we have a cylinder like this, and we're told the radius of the cylinder is r, and we're told the volume of the cylinder is 75 pi. So the volume of a cylinder, you kind of need to know the volumes of basic shapes. So the volume of a cylinder is pi r squared L. You need to be able to remember this. And we can create an equation here. 75 pi is equal to pi r squared L. So that's a very easy equation to make. But what are we actually going to do with this? Well, remember that L is the length of the cylinder. Now, L is not actually mentioned anywhere in the question. R is mentioned. It says that R is the radius of the cylinder, but L is nowhere mentioned. And in the final equation that we need to see, you can see that R is present, but L is not. So this is a clue, and what this suggests is that we're going to need to get rid of L at some point. And the way we can do this, and this is a kind of a tip that you should remember, it's really good, is we should create an equation for L using this equation. So therefore we can sub that in later on in order to get rid of any kind of L's we have in our final equation here in order to make it just in terms of R. So let's do that. Let's divide both sides by pi. Let's do 75 is equal to r squared L. Divide both sides by r squared to get 75 divided by r squared is equal to L. And we can sub this in later on for values of L in order to get the cost just in terms of R, and hopefully this will give the equation here. Okay, now let's move on to the surface area part. So we're told that the surface area of this glass cylinder, the cost of polishing it, is £2 per centimetre cubed for the curved surface area, so this is this part here, and it's £3 per centimetre cubed for the circular top and base. So this is this part here, and there's one at the back as well. So the key with this is it's per centimetre cubed. How much it's going to cost, it depends on the actual size of the surface area. So let's actually find the size of the surface area. So let's start with the circular part, so one here and one at the back as well. So the surface area is going to equal to, and they're just circles, so the area is just going to be pi r squared. But again, there's two of them. There's one here and there's one at the back. So it's going to be times 2. So it's going to be 2 pi r squared. And the cost of cleaning this is £3 per centimetre cubed. Remember, this is in centimetre squared, sorry. This is in centimetre squared. So therefore, it's £3 per centimetre squared. So therefore, the cost is going to be 3 times, and this is a centimetre squared, so it's going to be 2 pi r squared. It's going to be these times together, which is going to be 6 pi r squared. So that is the cost of cleaning the circular parts. So now we just have to do the curved surface area. The surface area of the curved part is going to be 2 pi rl. Again, this is something you're just going to have to remember. It's kind of the circumference of this circle and then expanded across the whole thing like that. So it's L. And therefore the cost of this is going to be £2 per centimetre cubed. So the cost is going to be 2 times 2 pi rl, which is equal to 4 pi rl. So now we have the total cost, so we just add these together. So the total cost is going to be C is equal to 6 pi r squared plus 4 pi rl. So this is the equation, however L is not present in the final equation, so we need to get rid of this L, and we can do this by using the equation that we mentioned before and subbing this in for L. So this is going to be equal to 6 pi r squared plus 4 pi r times L, so it's going to be times this, so 75 over r squared. We can simplify this, and this is going to be equal to 6 pi r squared, and it's going to be, so the r's are going to, so it's r here and then it's r squared in the denominator, so if you times these there's just going to be an r in the denominator, so it's going to be plus, and we'll do 4 pi, and then it's going to be times 75 over r, because this r is going to cancel out with this r to give 1r in the denominator, and this is going to be equal to 6 pi r squared plus, and then 4 times 75 is equal to 300, so it's going to be 300 pi over r. So C is equal to 6 pi r squared plus 300 pi over r, and you can see that this is the final equation. So this is the final answer. So for part B, we need to find the minimum cost of the polishing. So we need to find the minimum cost of C. And when it's a minimum cost, as I said before, they want you to do a derivative and then equal that to 0 to find a stationary point. So we need to find dC over D, and we're differentiating R. So dC over dr is equal to, and then we differentiate this, and we do it term by term. First of all, let's write this in a bit of an easier form to differentiate. Let's do C is equal to 6 pi r squared plus 300 pi r to the minus 1. Then we differentiate the terms individually. 6 pi r squared is going to be 6 pi times, and r squared differentiated is 2r, so that's going to be equal to 12 pi r, and then 300 pi r to the minus 1 is equal to 300 pi times, and then r to the minus 1 differentiated is minus r to the minus 2, so this is equal to minus 300 pi r to the minus 2. So dc over dr is 12 pi r minus 300 pi r to the minus 2, and then we're going to equal this to 0, and we need to find the value of r for when we equal this to 0. So let's do that. First I'm going to write it in the fraction form to make it a bit easier. So it's 12 pi r minus 300 pi over r squared, and this is equal to 0. First of all, I'm going to divide everything by 12 pi, because 300 is divisible by 12, and this gives r minus, and it's going to be 25 over r squared is equal to 0. Now, because r is in the denominator, we know that r is not equal to 0, otherwise we'd be dividing by 0, and that just doesn't work. So therefore we can times everything by r, and we can times everything by r squared more specifically to get this out of the denominator. So times everything by r squared to get r cubed minus 25 is equal to 0. But put the 25 on the other side to do r cubed is equal to 25. So therefore r is equal to the cube root of 25, which is equal to 2.924. Now, quite interestingly, I talked about obviously checking with your calculator in the previous differentiation videos. For this specific example, you can't actually do it because your calculator times out. That means that the equation is too complicated. That's the only example I've seen of this at A level, which is quite bizarre. But I just say that this is just one very kind of anomaly of a question. Most of the time it does work. So we've got r is equal to 2.924. So now what we have to do is then sub r into here to get the actual minimum cost, the minimum value of C. So C is going to be equal to 6 pi and then 2.924 squared plus 300 pi over 2.924, and if you put this into a calculator, this is equal to, it wants it to the nearest pound, it's equal to 48348.48, and the nearest pound will be rounded down to 483. So that's the minimum cost. So for part C, we need to justify that the answer that we've given is a minimum, because again, we've equaled this to 0 and found the stationary point here, but it could be a maximum or a point of inflection. So we need to prove that it's a minimum, and the way we do this is by finding the second derivative, plugging this value in, and if it's minimum, it should be positive. So the second derivative is going to be, and we differentiate these terms individually, so 12 pi r is just going to be 12 pi, as the r just goes away, and minus 300 pi r to the minus 2 is going to be minus 300 pi times, and then r to the minus 2 differentiated is minus 2 r to the minus 3, and this is equal to, the minuses cancel out, so this is going to be a positive number. It's going to be 600 pi r to the minus 3. So the second derivative is equal to 12 pi plus 600 pi r to the minus 3, and then we sub this value in, so it's going to be 12 pi plus 600 pi, and then we sub in this value of r, 2.924 to the power of minus 3, and if you do this and put it into a calculator, it gives out a value of 113.1, which is a positive number. So therefore, as it's a positive number, as the second derivative is positive, therefore it's going to be a minimum. Again, go back to the second derivatives video where we talked about why this is the case. So here's another modelling question. This time they give us the equation, we don't need to derive it ourselves, where c is the cost of the journey and v is the speed in which the vehicle is going at. And we need to find the value of v that minimises the cost of the journey. So as it minimises, it's telling us that we need to use stationary points. So we need to find the value where the derivative is 0, and then what the value of v is at that point. So we need to find the derivative. So first of all, let's write this in its indices form. So c is equal to 1500 v to the minus 1 plus 2 over 11 v plus 60, and then we can differentiate this. So this is going to be 1500 times minus v to the minus 2, which is going to be equal to minus 1500 v to the minus 2, and this is just going to become 2 over 11. So dc, because this is what we're differentiating, over dv, because this is what we're differentiating in terms of, is equal to minus 1500 v to the minus 2 plus 2 over 11, and then we equal this to 0, and then we need to find the value of v for which this is true. So first of all, let's write it in its fraction form. So it's going to be minus 1500 over v squared plus 2 over 11 is equal to 0. Again, as v is on the bottom, we know that v cannot be equal to 0, so therefore we can times everything by v squared to give minus 1500 plus 2 over 11 v squared is equal to 0. Move this onto the other side to get 2 over 11 v squared is equal to 1500, and then v squared is going to be 1500 divided by 2 over 11, which if you put into a calculator is equal to 8250, so therefore v is equal to 90.8 to 1 decimal place. Again, you can check your answer by putting this function into your calculator using the d over dx function and then putting 90.8 in as x, and it should give out a value close to 0. And then for part 2 of A, what we're just going to do is sub this value of V into here, and this will be the minimum value of C. So C is going to be 1500 over 90.8 plus 2 over 11, 90.8 plus 60, and if you put that into a calculator, that is equal to 93.03. So that's the minimum value. So for part B, we need to prove that this is the minimized value instead of the maximized or the point of inflection, and we do this using, it's telling us to do d squared c over dv squared. So the way we're going to do this is first of all find d squared c over dv squared, and this is going to be equal to this differentiated, so do it term by term. So this is going to be minus 1500 times, and then this differentiated is minus 2v to the minus 3, which is equal to 2 minuses cancel out, so it's going to be equal to 3000 v to the minus 3, and this term just goes away because it's a constant. So d squared c over dv squared is equal to 3000 v to the minus 3, and then we sub in this value of v, so 3000 90.8 to the power of minus 3, and if you put this value in, it gives out a really small value of 0.004, but this is bigger than 0, so it's positive, so therefore as it's positive, therefore it's going to be a minimum. So for question C, this is quite a weird question that they sometimes give to do with the model, in which you just need to find something wrong with the model. So just look at the model that they give you and just think of something like, in a real life scenario, how would this not work? How would this model not work? And in the mark scheme, they talk about the fact that you can't keep a steady speed throughout, because this is what this model says. It says that between the two destinations with the lorry, it stays at the same speed throughout, which obviously it can't do. So something like that, they're usually quite lenient with the marks for this. So just try and think of something that could be wrong with the model.